So let's come to the sort of the end of the story, and something you might remember. Yeah, Le Chatelier's principle. You know, you remember this from general chemistry, right? I mean, it's you probably do. What was it? I'll quote what the book says. A system at equilibrium but you know it's more general than that. I mean this the world is not at equilibrium, is it? No, fortunately. Uh, but it but well let me just finish what I'm going to say here. A system at equilibrium responds to a disturbance in a way that minimizes the effect. Oof, let me try again with that one. Okay, hold on. I'll translate it in just a second. You know, so this is why, you know, anyway. A system at equilibrium responds to a disturbance in a way that minimizes the effect of that disturbance. I mean, I'm kind of like that. You know, I don't like conflict. You know, if there's a problem that's brewing, you know, you try to settle it down. And you know, people use Le Chatelier's principle a lot. They say, well, you know, we can still let's burn as you know, let's keep burning a lot of petroleum because you know the world will respond to minimize the effect, right? And which you know is true. Le Chatelier's principle is a principle, and I don't really know the history, but it's probably one of these things which you know if you start looking into it, uh, sort of regularly amazing that you have these people way back that understood things somehow without all the tools that were then subsequently developed to understand it. So like with thermodynamics, we can talk about it fairly precisely, and we can derive some things. And yeah, of course, Le Chatelier. What's the big deal? But you know, he more likely predated all the machinery that you use to try to figure these things out. It's pretty impressive, you know, what people can do. But you know, you put CO2 in the atmosphere, and more trees grow. Hey, that sounds like a pretty nice thing, right? You know, we can have some nice green spaces, and that would be an example of this. And of course, that's a system that's not at equilibrium. It may be a steady state. You know, there's a lot more thermodynamics that one can talk about. Steady state, non-equilibrium thermodynamics, things like that. But let me give you an example that kind of makes sense. Like we have let's say we have the reaction A as a gas, and it's in equilibrium with 2B as a gas. And so if I wanted to draw this sort of cartoonishly, so the and you know this might be equal to this diatomic, or something like that. You know, A might be equal to B2. But you know that's just getting into the details of these molecules. But I have A, and 1 mole of A, if it completely reacted, would give me 2 moles of B. So I can draw a picture. I have some A still in there, and then I've got some B in there. Let's see, 1, 2, 3. Let's get the right number. And I've got a movable piston, and I've got an external pressure. So that stuff's in there. There's a pressure that has, and I have an external pressure. Everything is in balance, right? And now along comes the disturbance. I increase P external. And so the way I would do that in this case, I would, like, let's say, decrease the volume. And what do you think happens to this equilibrium? I mean, just common sense, let's say. Forget about anything you learned in here, because it just distracts you from using what you already know. I mean, you think things are going to change? Yes, they are. So we could either have exactly the same situation, or the reaction could go backwards or forwards. But let's say it went forward. So even more of this, so I increase the pressure, and then the gas goes even forward and makes more gas, and then that even raises the pressure. So this is a very unstable situation, isn't it? Like, Le Chatelier's principle is related to the stability of matter even. But what will happen is the reaction will shift, and we'll push it back the way it came. So I increase the pressure. There's a reaction that makes things that can increase the pressure, but it shifts backwards to produce fewer molecules that would contribute to the pressure going up. So the reaction shifts to the left as this pressure is increased. So that's an example of Le Chatelier's principle. So, you know, we do this, push it back the way it came. I hope that makes sense. Does it? Wait. Reaction shifts to left as pressure is increased. So not only is the handwriting poor, but the grammar isn't that good either. So you know, it's just a you know, so. But don't worry, next quarter. Who teaches next quarter? Is it Potma? Potma, yeah. He's a cool guy. He's the kind of person that wears red tennis shoes, red Vans and things like that. You know what I'm talking about? Yeah. You know, everybody keeps getting older, and he does too. But yeah, he's this very interesting Dutch guy, and he makes it all. So you'll enjoy him. It could be a lot worse. Let's put it that way. So I'm not sure who does the third quarter in this class. Not me. What? Mukamel? Is it Mukamel? Guh. Okay. Yeah. Okay. That'll be interesting too. So anyway, no, it's good. All good. So there's a similar effect with increase. Well, let's say, I would say increase, because you know there's always when there's a knob you can turn it both ways, right? So let's say change in temperature. And you know, lurking in our mind, there's always the Gibbs free energy, right, which is a function of temperature and pressure. So you know, if we talk about knobs we can turn, we can change the pressure, we can change the temperature, and then we can look at what Gibbs tells us. So if I have reactants and I have products, let's say, okay, so that there's actually three cases, but let's look at like, for example, delta H for that reaction is greater than, oops. You know, if you delay it all, drawing your symbol, it thinks you're going to draw a straight line. Anyway, delta H greater than 0. What does that mean? What kind of reaction is that? Endothermic, right, because you want to put heat in. It wants heat to go in, right? And so if I increase the temperature, do you think happens? Yeah, this shifts to the products. That makes sense, right? And if I have delta reaction H less than 0, so this is exothermic. X enthalpic, so it's hard enough to pronounce exothermic, so we'll stick with with this. Then increase temperature leads to shift to reactants. So heat is, like, whether it be reactants or products, heat is absorbed. I raise the temperature, there's some heat available, and it's absorbed by the system. And by putting heat into the system, if it's endothermic versus exothermic, it will shift it to the products or the reactants. Sort of opposing. It's like your cat, right? Or I don't have a cat. Dogs are not really governed by thermodynamics, but maybe cats are. They just don't want to do what you're trying to make them do, so they oppose it to compensate. So we can do some math. And here's another equation with a name associated with it that I would never remember. Clausius-Clapeyron was now I will never forget because of my friend and colleague, Professor Shaka. But like if someone said this to me, I'd have to go and look it up. I just don't remember stuff like that. So by the way, should we have any terms on the final? Are you over that? What? Would make it easy? More terms, but then what happens is you say something that could well be true, but maybe it doesn't get the points you think. So let's not have any terms, okay? This way we can have more other things. So what? I'm kind of over the terms, aren't you? Yeah. I don't know what I'm sort of out of ones. I'd have to repeat them, But there's the terms are easy, but okay. So terms are easy because you just have to know what to say for the term, but they can go wrong on you, can't they? And if they go wrong on you, it's not really. It starts being just random errors, like oops, I said the wrong thing, rather than I understand or don't thermodynamics. So I like terms because people just write equations without knowing what they're doing. That's a pet peeve of mine, and you can find it. It's very easy to find. It's like people that say now when you go in and get a cup of coffee, I'd like a small coffee. And what do they say? Perfect. Have you noticed that? I feel like Larry David here. But there's a pandemic which is even more contagious than the COVID, which is people that say perfect whenever you say anything. And the worst thing about it is I started doing it because this is how I know it's so contagious. But anyway, why am I even talking about this? I think the terms, are just mainly easy, but a minefield, and then you can lose some points which you don't want to lose. So let's ditch them for now. So let's go back to remember we have delta G for the reaction is delta G standard state plus RT log Q, right? And remember this Q can be let's write an equation. I'm getting my symbol. Let's write an equation that maybe you don't like, but is the general one. It's that product of the activities raised to the stoichiometric coefficients. But for gases, it would be, the product, I'll keep using that, P sub j over P standard to the nu sub j. Okay. So that's true in general. Like I'm reviewing here, right? I take some gases, I make a cocktail out of the gases. I mix some, I mix some H2 and O2, and maybe I throw a little water vapor in there to start with. But maybe if I just had pure H2 and O2 together, and I mix them, and I calculate, and so there's partial pressures of those ingredients. I calculate Q, and I get a number, right? I put it in here, and I get a delta G for the reaction. And perhaps this thing's positive or negative. If it's negative with the initial mixture, then what's going to happen? You know, you mix some gases. You calculate Q. You calculate delta G at standard conditions, you know, from some tables, and you calculate this object, and you get a negative delta sub R G. Multiple choice question. What happens? A, the reaction, A, nothing happens. B, the reaction proceeds in a forward direction as written. C, the reaction proceeds in the reverse direction. And then just to see if anybody's hasn't been coming at all. D, the entropy of the universe decreases. Those are your choices. What do you pick? I mean, the reaction, what? Yeah, the reaction proceeds in a forward direction, right? Because you can lower the delta G, and you know, there's all this derivation. There's a formula, nu sub G mu, you know, nu sub J mu sub J summed over J is that delta sub R of G. I'm not going to write that down. You've seen it before. So that's what happens. But of course, when I have 0 for that, so, you know, K is nothing but Q, you know, at equilibrium. Right, that's, is it, do you still call it Twitter? Yeah. Well, who came up with this idea of calling it X anyway? Elon Musk. Okay. Anyway, so yeah, I wonder if I got to check to see if this is taken, because that would be good. But at equilibrium, Q happens to have a value that makes this true, and we call it the equilibrium constant, right? And then, you know, if I happen to mix, let's say I mixed a cocktail of gases, and this would be very fortuitous. If this happens, go out and buy a lottery ticket, right? But if you mix some gases and you calculate that delta G of reaction, you get 0. Then, you know, then there's the multiple choice question. What happens? You mix some gases, you calculate delta G of the reaction, and it's 0. Now nothing happens, right? Because you're at equilibrium. And then that Q that you concocted is actually equal to K. So my K, I can just solve for that. And you know, if you have the wrong person teaching your general chemistry, they'll give you numbers where they put that in your calculator, it's too big to exponentiate. But no one would ever do that, would they? So, so that's an expression for an equilibrium constant if you had all those ingredients. So okay, let's get back to, how do you say this? Van 't Hoff? Van 't Hoff? Yeah, I have so ask Eric Potma, because he's from the Netherlands. And that seems, I'm pretty sure that's where Van 't Hoff is from. If you ask someone from the Netherlands how to pronounce anything, you listen carefully and you still can't do it. Right, that's been my experience. But let's get back to that equation here. And so if I just took the log of this, I would have this, right? And I could write this as minus 1 over R delta reaction of G, that thing, you know, naught over T. Okay. So I'm just grouping things here. And I could then take the derivative. Okay, so why am I taking, I always say this and I'm maybe not following it. Why am I doing all this math? Good question. Let's go back up and remind what I said. Similar effect with change in temperature, okay? So then I talked about this sort of intuitive thing of endothermic and exothermic. And what I'm trying to do here is I want to know what happens if I change the temperature. I want to see what Le Chatelier somehow understood about if I change something, how a system responds to mitigate the effect of that disturbance. So that idea here becomes quantitative by saying, okay, I'm going to change the temperature, and I want to see what happens to the chemical equilibrium. Okay, so if I have K, and you knew this from general chemistry, if I give you a numerical value of K, you can do a problem, some more pleasant than others, where you figure out how much reactants and products you have at the end, right? So numerical value of K, reactants and products are determined, you know, given, you know, all the data you're given. So I change the temperature, and now I want to know how the reaction responds to that. And one way you can do that is you can see how the equilibrium constant changes if I vary the temperature. So I want to know the dependence of K on temperature. I'm going to look at how it changes. And, you know, why did I take the derivative of log of K? Because, you know, 100 years ago someone did this problem and they decided that that's the cleanest way to do it, okay? So if I know how log of K depends on temperature, I know how K depends on temperature. And on the right-hand side, there's something that maybe I can get some traction out of. And now I remember, I would have remembered from, let me write just the answer down. Again, this is a named equation. And you all remember this, don't you, from Focus 3? And you know, you wouldn't have remembered it anyway, probably. But I didn't mention it. I didn't go over this then. So we can derive this. And again, this is a little bit of review, right? We're going back and looking at possible problems that one could possibly have done earlier in the class. But let's derive this, okay? So just for fun, right? You could, you know, probably if I told you, you might believe me, but let's take this as a reason to just review some things, right? So I have G, and G is a function of TP and N's, because it depends on you know, more than one component. So you know, N's means, you know, N1, N2, N sub R, right? This is my shorthand. So I'm just taking a function and taking its derivative with respect to everything it depends on. Right, and you'll remember that these partial derivatives have their nicknames. So dg is minus s dt plus v dp from back in the good old days when we just had one ideal gas. But then we have this sum over j, mu sub j, dn sub j. And okay, that's generally true. But my partial g, partial t, at constant pressure, and also the n's, is minus s, right? And, we could do, okay, now Maxwell's equations rear their ugly head, and we can derive some Maxwell equation. But let's not do that at this point. Let's control ourselves. I also know that g is h minus ts, right? So I can rearrange that and use that, and I can write partial g, partial t at constant p as g minus h over t. And so if I had what is it? So if I take the derivative, so that tells me what dg dt partial g partial t is, but not using that independently of that, okay. If I want to take the derivative with respect to t of g over t at constant p, then this is the quotient rule from calculus is what I'm going to use. So there's the numerator and the denominator. I'm going to take the derivative of the numerator and then divide it by the denominator. So that would be 1 over t, partial g, partial t at constant p. And then I have to leave the g and not take its derivative, but I need to take the derivative of 1 over t. And that's a minus 1 over t squared times just the g floating around. So I did some calculus, and so my partial g over t, this is not a spectator sport, I understand that, but we have to watch it. So my son ended up working at the national pickleball competition in San Clemente. Did you know there is such a thing? Yeah, pickleball. Do you know what pickleball is? Yeah, well, if you're not 60, I don't think you should know. I mean, it's one of those sports. If you had invented a sport to be part of a Monty Python movie, you would have invented pickleball. So my son was at this pickleball tournament in San Clemente, and it was actually on ESPN. I watched a little bit, see if I could see him there. He wasn't playing. Okay, let's get that straight. And I learned that pickleball is also really not a spectator sport, but it's not as bad as this. Okay, so if I go through this and I work out, let me sort of suggest where I'm going with this. I can write this here, this one from above, is factoring out a 1 over t. Right, so there's a 1 over t factor, and then there's this first term, flashlight, first term, and then the 1 over t squared, there's a 1 over t and a minus 1 over t. Okay. So I can use what I had up, all my ingredients up here, and I can write this thing. Now I'm kind of crowding in my own space, as let's put all the arithmetic in. And you know, this is 1 over t minus s, right? That's that first term. And then there's this minus h minus t s over t. And so the whole thing at the end of the day, and this is where we were going, is minus h over t squared. And so that, you know, that's true for the state function g. And then, you know, if we look at, you know, delta rg at, you know, with this superscript, then we're taking differences of two things that are equal to that, and we're doing it at standard state. And so what we end up with is d delta rg over t dt, right, a constant p. That's equal to delta rh, that thing, over t squared. And, you know, if we were mathematicians, we would put, I don't know if they still do this, but QED, which stands for something in Latin, which I never took. So, like quo something demonstrandum. I don't know, those of you who took Latin, and I know you're out there, are laughing. But it meant, that is what we meant, that this is what we set out to show. And this is what we set out to show. So, at the end of the day, what we determined and there's a plus here, note, because there was a minus and now there's another minus. And remember, it's the signs that will get you. So the change in log K with respect to temperature is just the delta H of the reaction at the standard conditions divided by RT squared, okay? And like if as promised from our first discussion, if delta sub R H at standard conditions is positive, so it's endothermic, and I raise the temperature, right? So the dt in the denominator of the derivative, then that means the log K gets bigger. And if logarithm is a monotonic function, so you got to worry about logarithms. They're dangerous if you take log of 0 and things like that. But as long as K is not 0, you can take the log. It can be, a positive, log of this thing can be positive or negative. But if I increase the log K, I also increase K. So that tells me if I have an endothermic reaction and I raise the temperature, the equilibrium constant increases, as we sort of intuited. And we can integrate this, and we'll assume that delta RH, this thing, is a constant over the range in temperatures of the integral. And that's roughly true. And I'm not going to do the integral. If we do the integral, so we're integrating log K from one state to another one, and the integral of d log K is log K at the two limits. What? Okay, it's story time. Let me read. Assume this thing is a constant over the range in temperature. Okay? Yeah, yeah. You know, like if this were an engineering class, I'm picking on the engineers again. Like you might have the reaction, you know, for this process, you know, for this process that goes on in the industrial synthesis of this stuff, which is carcinogenic, but we're going to sell it anyway, right? If we raise the temperature, how do we shift the equilibrium? You know, but it costs money to raise, you know, to raise the temperature. But the enthalpy of the reaction is given by this power series with these empirical coefficients and some weird expression that gives that delta H in terms of a 1 over T and a log T and a T to the 1.4 power, you know, some complicated fit to some experimental data for how that H depends on temperature, because it will, more than likely. It's only for the ideal situations that maybe it does depend, but it's simple. Because you know that H for an ideal gas is 5/2 RT, right? So how can we say that it's constant? But it is for this carcinogenic stuff that the company's trying to make, okay? And so, but by assuming it's constant, we can do the integral without doing a lot of work. It factors out. So we have to integrate 1 over T squared, right? Because that's what's on the right-hand side. And the integral of 1 over T squared is minus 1 over T. Because if I take the derivative of minus 1 over T, that's the integral, the derivative of minus T to the minus 1. A minus 1 comes down to get rid of the minus sign that was there, and then I get a T to the minus 2. So I check my integral by doing the derivative. And so that's why on the right-hand side, we get a minus delta H sub reaction over R, and then a 1 over T2 minus a 1 over T1. So that's just what you get when you do the integral. So, and like I said, and this will be the last thing I'll say. You know, so if delta H is greater than 0, well, and I can rearrange this. I'll put a plus here, and you know, this is dangerous to do. But if I put a plus, then I can put a 1 over T1 minus 1 over T2. So I swap those terms, and I just put a sign out there. So let's say T2 is greater than T1. So I'm raising the temperature. So that means 1 over T1 minus 1 over T2 is greater than 0, right? Because the denominator of the second term, which is negative, is bigger. And so I'm not, you know, this is the signs again, you know, but this quantity is positive. And so that means that, like endothermic, you know, K2 is greater than K1. And if delta sub R H, this thing is negative, so it's exothermic, then K2 is less than K1. So the reaction is shift to products, and this is shift to reactants. And I don't know if it was intuitive or not, but that was what that's what we reasoned with common sense at the beginning, right? So you can prove that by using this construction. Okay, that's enough for chemical reactions. You might say, well, you could have given us a lot of problems. I did give you a problem about this N2O4 dissociation. This is a standard problem. And I'll give you the solutions, hopefully today, where you could, that problem is more like a mini project. So I would never put that problem on the exam, because it's just too many places to make mistakes. But the other ones I gave you on problem set 6, I think it was 6. Yeah, there are ones with V naughts and V naught over 2s. Those are good problems, and I'll talk about one of those on Friday too. I'll work one of those, because it's illuminating to look at the thinking that goes into it. All right, so let's get out of here. See you Friday. Yeah. Yeah.